Dear colleagues and friends, ladies and gentlemen, salam. It is my great pleasure, and on behalf of the Electronics Department of the Faculty of Technology, to welcome all of you to participate in the 2023 National Conference on Emerging Technologies in Electrical Engineering. وخير ما نبدأ به آيات من الذكر سورة الفاتحة. أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. الحمد لله رب العالمين الرحمن الرحيم مالك يوم الدين إياك نعبد وإياك نستعين اهدنا الصراط المستقيم صراط الذين أنعمت عليهم غير المغضوب عليهم ولا الضالين. نرجو الآن من السادة الحاضرين القيام والاستماع للنشيد الأول. I'm grateful to the University President, to the Dean of the Faculty of Technology, and to all the speakers who have joined us today to share their research works and experiences with us. The conference will cover all areas of electrical engineering, such as power, electrical systems and renewable energy, electrical machines and actuators, robotics, automation and control systems, telecommunication systems, signal, image and video processing, and so on. Among the 200 received papers, the organizing committee has selected 114 papers. The conference program is organized as follows. We start with a plenary session conducted by Professor Mekhilef from Swinburn University of Technology, Melbourne, Australia. We will have poster sessions after that, and we will have oral sessions that have been delayed for some reasons. And we will have also virtual sessions. In the second day, we will have another plenary session conducted by Professor from the University of NCETEE'23, and we'll proceed to the oral sessions and some virtual sessions, and then there will be closing ceremony. Without further delay, I call Professor Fatah to give an introduction to the conference.
Thank you. Mr. Rector, Vice Rectors, Deans, and Head of Department, dear guests, dear participants, good morning and salam alaikum. It's a pleasure to welcome everyone to our NCETE 2023 conference. I would like to extend a special welcome to our guest of honor, Professor Mekhilef from Australia, who will be speaking later. We couldn't make today a reality without the hard work of the organizing committee and dedication and help of the Dean of the Faculty of Technology, Professor Farid Hamad. Thank you again, and I wish you enjoy and take this opportunity to share your ideas and research work. Thank you again.
We invite now Professor Farid Hamad, Dean of the Faculty of Technology, to give a short speech.
بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف المرسلين سيدنا ونبينا محمد خاتم الأنبياء والمرسلين. أستاذ الفاضل السيد مدير الجامعة مثلا، السيد رئيس قسم الإلكترونيك، السيد رئيس قسم التعليم الأساسي للتكنولوجيا، السيد مسؤول حاضنة المشاريع لجامعة الأحد عباس واحد، زملاء الأساتذة، باحثين، طلبة الدكتوراه وأساتذة من مختلف أنحاء الوطن. السلام عليكم ورحمة الله تعالى وبركاته. إذا نلتقي اليوم في هذا الملتقى العلمي الأول من تنظيم قسم الإلكترونيك، والذي سيلتقي فيه باحثين من مختلف جامعات الوطن لتدارس ومناقشة آخر التطورات في مجالات متعددة التي تخص الإلكترونيك وتطوراته على المستوى الوطني وعلى المستوى الدولي. بهذه المناسبة أشكر لجنة التنظيم وعلى رأسها الأستاذ كريم فاتح على تنظيم هذا الملتقى الأول في قسم الإلكترونيك. هذا شيء فرحنا بزاف، لأنه أول ملتقى نتمنى أن تكون في ملتقيات مستقبلا. الحمد لله أنه في المجلس العلمي اللي فات كان ثاني اقتراح تنظيم ملتقى دولي. شكرا لكم أستاذ ولكل القائمين على تنظيم هذا الملتقى. نتمنى لكم النجاح والتوفيق باسمكم وجميعا. وأرحب بالأستاذ سعد مخيلف، هو ابن جامعة الصيف وابن ولاية الصيف، اللي شرفنا بحضوره. تلاقينا معه في ملتقى دولي جامعة ماليزيا من جامعة أستراليا. بكم نفتخر أستاذ الكريم. شكرا لكم. وبالمناسبة الأستاذ السيد مدير الجامعة لإعلان الافتتاح الرسمي للملتقى. تفضلوا. شكرا لكم.
شكرا مشترين. بسم الله الرحمن الرحيم، والصلاة والسلام على نبينا الكريم. أستاذي السيد عميد الكلية، ضيوفنا الكرام، ضيفنا الكريم الذي جاءنا من بعيد، أستاذ سعد، يشرفنا بالحضور الفعال في هذا الملتقى. السادة المسؤولين على مستوى الكلية والجامعة، السادة والسيدات المنظمون لهذا الملتقى الكبير من ناحية الحجم. والله إنه شاهدت البرنامج، يعني فيري هيوج اللي يشمل كثير من الجوانب تاع المساحة العالمية. شكرا على هذا المجهود وتنظيم هذا الملتقى الوطني. السيدات والسادة الحضور المعلمون اللي جاءوا من العديد من الجامعات الوطنية وأسرة القسم نتاع الإلكترونيك وكلمة نتاع الهندسة الكهربائية بجامعة ستيف. كل الحضور الاسمية والقادمين، السلام عليكم ورحمة الله تعالى. والله نجد مسؤول في هذه الأيام لحضوري وللعديد من اللقاءات العلمية من الكثير من هذه الكلية الناشطة في مختلف الفروع بتاعها. كنا التقينا في لقاءات علمية ضد المتحف والطاقات المتجددة والتحولات الكيميائية والمسار الكيميائية والجدال إلى آخره. اليوم في هذا اللقاء اللي يتكلم فيه على الهندسة الكهربائية بالمفهوم نتاعها، المقاربات والتكنولوجيات الصاعدة في هذا الميدان التكنولوجي النشاط في العالم الخارجي. والجينيتي كما يقول خاصة الميكرو ميجا ودرك نقول النانو ميجا اللي نمشيو من الانفينيموفيكي للجيغوفاسك من لي باور سيستمز لي جيغا وات لا ميز ان اوف لوتيليزاسيون تاعها للآليات والتحكم فيها للسمع la robotique et le contrôle des systèmes embarqués, des systèmes, etc. Donc, كل المكونات ومن باب هذه المكونات les avancées وحنا نتكلموا على التكنولوجيات الصاعدة التكنولوجيا الجديدة في ميدان اللي هو في الحقيقة الآن أصبح مثل ما هو الحال في الذكاء الاصطناعي وأمور أخرى. الإلكترونيات والتطبيقات نتاعها أصبحت في ميدان أفقي اللي نوجدوه في كل الميادين نتاع التكنولوجيات الصناعية وأخرى في الكيمياء والصيدلية والصحة إلى آخره. إذن التطور اللي هو نشارك فيه هو عبارة عن التطور تاع كل التكنولوجيات في كل الميادين. نتمنى إن شاء الله توفيق، كل التوفيق في الأعمال بتاعتنا، وإن شاء الله نخليو بصمة ونسجلوا هدف الديناميكية اللي تعيشه الجامعة حتى الناس تصبح واحد في المشاركة تاعها وترك البصمات في الميادين التي هي تنشر فيها. إن شاء الله نتمشوا مع التطور تاع العلوم والتكنولوجيات اللي هي يعني تسارع في العمل. نشكركم على المجهود وعلى دعوة الفاعلين لا سيما من أبناء الوطن اللي هما في الهجرة في جامعة كبيرة والشبكة تاع الأساتذة والباحثين في الجامعة الجزائرية في الميادين اللي تعمل الحياة. إذن بارك الله فيكم وربي يحفظكم، وماذا تركوا لي الشرف لنا على الإطلاق الأعمال، فأنا أقول عن انطلاق الأعمال في هذا اللقاء الوطني للتكنولوجيات الحديثة في الهندسة الكهربائية. شكرا لكم على الإصغاء، شكرا لكم على المشاركة، ووفقكم الله في العمل بتاعكم. السلام عليكم.
I call Professor Karim and Dr. Afwaj to chair the plenary session.
Ready?
I'm ready.
Okay. Before giving Professor, it's a great honor for us to listen to you and to listen to your presentation. Before I give you the floor, I present rapidly Professor Mekhilef. Professor Mekhilef is an IEEE and NCETEE fellow. He is a distinguished professor at the School of Science, Computing and Engineering Technologies in Swinburn, University of Technology, Melbourne, Australia. He is an honorary professor at the Department of Electrical Engineering at the University of Malaya and a distinguished visiting professor at the Institute of Sustainable Energy, University of Naga, National Malaysia. He authors and co-authors more than 600 publications in academic journals and proceedings, 5 books with more than 7,000 citations, and more than 85 PhD students who graduated under his supervision. He serves as an editorial board member for many top journals, such as EAA Transaction and Power Electronics, EAA Opening Journal in Industrial Electronics, EIT Renewable Power, in Energy Power and Generation, ICRIM, Journal of Power Electronics, and International Journal of Circuit Theory and Application. Professor Mekhilef has been listed by Thomson Reuters Credit Analytics as one of the most highly seated in the top 1% in engineering research. He also listed in the world top 200% of science by Stanford University, USA. He is actively involved in industrial consultancy for major corporations in the power electronics and renewable energy projects. His research interests include power conversion techniques, control of power converter, maximum power tracking, and renewable energy and energy efficiency. Professor, you have the floor.
Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning. It's always a pleasure to be here in State. Prof. Steven was my teacher. He was teaching me in my lecture. I'm very proud. I'm his student, So what I have achieved is because of NCC, and all the lecturers at University of Sydney. Okay? What we have achieved is all due to our teachers and all the work they have done to us. And when he sent an email, asked me to come and give a lecture, you know. And I say yes. And I make my time to come and inshallah to share with you what I have learned. You know. And it's always to see good friends, you know, here. And so what I'm going to share with you this morning is about the role of power electronics. You know, power electronics is a very dynamic topic which is evolving and emerging. You know, and a lot of innovations have been done in this area. And how we can achieve this what we call neutral carbon society, because that's the trend. Increasing day after day, you know, how we achieve a neutral carbon society. And what I'm going to show you is how we, engineers, can play a role in this change, or what we call energy transition. So I start with some questions. Is why climate sustainability is challenged? Climate sustainability is very challenging, very complex, and because it's always comes with challenging compromise that you have to make. For example, the need of energy and the energy emissions. So when we need the energy, we need to burn oil and gas. On the other hand, we will generate carbon emissions. So human beings is always in a difficult situation on how to sustain, you know, how to meet the needs, but on the other hand, you have to sustain the climate and reduce the emissions. And for the last 100 years, there is a lot of what I call programs and what I call meetings and summits to try to reduce the carbon emissions. And I will show you some of the disasters. We've seen unprecedented disasters everywhere. So what we see this kind of floods happens not only in certain regions, but across the continent, across the world, you know, from Africa to China to the United States to everywhere. This is not used to be in the last 50, 60 years. We see this kind of situations everywhere. We see this 2020, you know, in Pakistan, you know, one of the largest floods. 5 million people have been displaced. 5 million people, hundreds of thousands of people died. Never happened before. So these kind of situations, we see this. We see it in everywhere. So, for example, in the United States, states which never been experiencing floods, right? We see this kind of in New Zealand and even in Australia last year. We had a flood which we never had before in the last 100 years. Never before. Before the floods, we had what they call bushfires. I think I don't know if you heard about it in 2018. We had a lot of bushfires. So we see this in New York, even in New York, you know. So we see this kind of disasters. And also, if we don't see the floods, we see this drought. I'm not sure you have been here or not. This is in China, in Yangtze River. Yangtze River, I have been to this place. It's in the center of China, where the largest power hydro in the world, 80 gigawatts. They built this hydropower plant in China to control the floods. Last 2020, what happened to it? Part of this river that supply this large hydro dried out. So we see this kind of natural disasters happening almost everywhere. And if you also see this, wildlife fires. So it is in the United States, you know, in Arizona, in California, fires that have never been before. And you can see this very close to us in Algeria, and even in Algeria happens before. So we see this, France, Portugal, Germany, Greece, Spain, Italy, all the whole Europe on fire. This never happened before before in the last 100 years. So what we can see is, we can see that actually, even in Siberia, one of the coldest places, we have this kind of fire. So this is an alarming, what I call signals, that we need to do something. We need to act, and we have to act fast. Because if we continue this way, we will reach to a stage, we call it the irreversible state. The irreversible state means whatever you do is too late. You can't change anymore. Whatever you do. So if we want to act, we want to have to act today, not tomorrow. So that's actually the state. And in Algeria, last year, I've expected this, it reached almost 53, degrees, That never happened before. So we can see this kind of signals, these kind of indicators that shows actually the climate is changing, and it's changing very fast, and we need to do some acts. We see also disasters, even snowstorms everywhere. So what's the cause of this? What are all the cause of these problems? The cause of this is the emissions that we generate. The CO2 emissions that generated from our energy use and our energy consumption. And I think you all know that the energy consumption per person is increasing. I think increasing, right? I came from a very small village in the northern part of the city. A small area, I don't know, maybe some of you have been there, It's an area which is the three villages, Jijun, State, and Mina. I think a place called Welban. That's my first primary school. I did my primary school in that area, a very isolated area. Now it's famous of Schwab. Schwab of Welban, very touristic place. In that place, in that village, the whole village in the 70s, talking about 1974, 1975, from 50 years ago, there is only one car. One car. The whole village. And that car used for everything, as a ambulance. If someone gets married, you have to bring the bride in it. If someone is urgent, you have to go to that car. One car in the whole village, and that person, very important person. It's more than the chef Daira or the Gweli. That's very important. He has a car, So everyone is. I went to the same place 40 years later. To the same village. What I found, every house, there are 3-4 cars. What does this mean? From the economic point of view, maybe people get richer. The economy is good. People are getting well. But from energy perspective, for me, I look from the energy perspective, the consumption per person has increased. Last time, one village, one car. Now, one house, 3 cars. So, the energy consumption is increasing. You just imagine, 20 years ago, how many of you have a mobile phone? No, none. Today, no one without a phone. So that's energy. You need energy to run this phone. How many laptops? So the energy consumption per person is increasing. So when the energy consumption, so there will be emissions. And what you can see, the level of emissions is, was stable until the last century. You can see there is a big jump. So this actually giving us another warning. This is the history. For the last thousands of years, the level of carbons was below the. So, and you can see it's an exponential increase of all the last 200 years. The earth temperature also is increasing, and that's why we have this Paris summit. We have the COP18 in Glasgow, and then everywhere trying to limit the earth temperature. So and this is the impact of this, the earth temperature. Maybe in Algeria we couldn't see it, but if you go to some countries, you can see the impact of this. I went to this Bangladesh. Bangladesh is a very poor country. During the rainy season, 25% of the land of Bangladesh goes underwater. 25%. Can you imagine 25% of Algeria goes underwater? The Pacific Islands, you know, in Australia, between Indonesia and Australia, there's a lot of islands. We call them the Pacific Islands. You know, one of them, maybe I give you an example, Maldives. I don't know how many of you have been to Maldives. Maldives is a very good place for tourists, but very expensive. You know, the highest level from the sea, it's around 5 meters. Means the whole country will disappear actually if the sea level goes. Right? And it's increasing, and this will lead to the increase of the sea level. Okay, who is the problem? Where the problem comes from? It comes from developed countries. They are trying to reduce. You can see the mature economies, they are already trying to reduce. But the emerging, like India and China, is contributing a lot to these emissions. Currently, now. But in the history, is the other way. History, you can see 23 rich countries contributed more than 50% of the carbon. So we're talking about the United States, Europe, Japan, Australia, and so on. And the other 50% is contributed by another 150 countries. So this is the history. Who is responsible for this? Who is responsible is all the developed countries. Okay, so that's in terms of history. So how we address this problem? We have a problem. So how we are going to address this? How we are going to solve this? Because there is no point of saying this is United States, this is Japan. No, now we need to solve this problem and address this. There are 3 ways how we can address these problems. Either mitigation, we have to mitigate, means slow down the impact. We can see the carbon emissions, we have to slow down the impact. Second one, we have to adapt, means you have to learn how to live with it. And the last one, which is the climate resilience, which is prepared to recover quickly as much as possible. So that's actually the 3 ways. Let me, one of the plans which have been discussed anywhere, which is called energy transition, okay, which is the increase of renewables in our electricity supply. Okay, and that's the target. The target is we want to reach up to 90% of renewables. And there are many countries that have already reached to 90%. I give you an example. In Australia, we have reached to 90% of renewables in our electricity supply. But there are many other countries which need to go for it. So it's expensive. In order for us, we need to reduce the amount of traditional fossil fuel in our electricity supplies. So that's the plan. Let me tell you this. This is my startup. This is all the introductions. Now we talk about this. This is a very important slide. It shows the load and the source. Okay? What we have here? If you look into here, what you can see. I don't know the monitor is. So what you can see on the right hand side, you can see all the load, different types of loads. We have, for example, we have appliances, TVs, lines, motors, automation, industry, power supplies, and so on. These are loads. Okay, on the other side here is the sources, where you can see the different types of sources. You can see the different types of sources here. They can be from storage, they can be from wind, from solar, from different types. What's the main common part here? The common is this block here, okay? You see this block here? These blocks, the blue blocks here, dark blue. These are dark blocks. These are, what is this? These are our power electronics. Now, when you go and go to the shop and buy an air conditioning, what they do? This is conventional air conditioning. This is an inverter-based air conditioning. When you go and buy a fridge, they will tell you this is a normal fridge. This is an inverter-based. You go and buy a washing machine. This is a washing machine normal. This is an inverter-based. You go and buy lamps. This is an LED. This is normal. What's the difference? What is inverter-based? This is electronics. So all the appliances that we use today are all power electronics driven. Every appliance, just name it, any device that we have, it has a power electronics in it. electronics helps to reduce the energy consumption. So that's why we use the inverter inside the air conditioning system, because we want to reduce the energy consumption. We want to use it in the washing machine because we want to reduce the energy consumption, right? So that's the main, that's the idea. So from all the loads, 99% it's power electronics driven. We're talking about electric vehicles now. We're talking about electric aircraft. So electrifications can only happen through power electronics. Okay, so that's from the load side. If you look into the source side, the other side, this side, the left-hand side, what you can see also, photovoltaic. Photovoltaic will never work without inverters. Right? We never work without power electronics. Electric vehicles, storage, we never work without power electronics. So what you can see is a dominance of power electronics on the source side and also on the load side. So, and I will give you some examples, how we can make this impact. So I'm going to explain how power electronics can help reduce the energy that we consume and also we use. Let me give you this. This is the power supply. This is actually a laptop power supply. I don't know, all of us have this, right? So usually we have AC, we have around between 9 volt to 19 volt DC, and then it goes to the laptop. In the laptop, there is a converters and the voltage regulators. This is for the display, this is for the disk drive, this is for different memory. So different voltage levels required inside the laptop. You understand? This is clear. So from the AC, we generate this, and we have it. Different requirements of voltage. I'm going to give you an example of how this is the circuit diagram of the power electronics. This is the circuit diagram that we use in these power supplies. Very simple one. Very simple circuit. We have the drop between around 400, between 240 volts, and then we convert to generate the DC. So what changes? And this one usually used to be a hard switch. Hard switch. So what actually we did 20 years back, so we moved from hard switching to soft switching. Just this change. We had these capacitors and these inductors to create the resonance, and switch at low, zero voltage, zero current switching, and increase the frequency from 50 kilohertz to gigahertz level. So we can reduce the size of the capacitors and the inductors. Let me show you the impact. It was the maximum efficiency of the hard switching power supplies was around 85%. Maximum efficiency. So what does this? 15% losses. 15%. I know the power of this is around 70 watts. Let's assume it 100 watts. So for every 100 watts, we lost 15 watts. Is it a lot? 15 watts. Not much, right? But multiply by how many laptops we have around the world? Billions? 15 multiplied by 1 billion. You can see the amount of saving that you can do. So you cannot look at your scale level, you have to look globally. So let's see, let me give you some statistics. So it improved 2009, improved around 90%, 2010, 2011, 2012, and we reached around 95% efficiency. Just changing from hard switching to soft switching. Very small capacitors and small inductors. So this is the amount of saving. So how much is the amount of saving? The amount of saving is more than 20% improvement in over 8 years. And what is the amount of electricity? The amount of electricity we save by this improvement is equivalent to what is generated by 60 nuclear power plants. 60 nuclear power plants. One nuclear power plant can generate, usually nuclear power plants are between 900 megawatt to 1 gigawatt size. Nuclear power plant, usually around 1 gigawatt. one nuclear power plant to be able to generate around 7 trillion watt-hour of electricity per year. 7 trillion watt-hour of electricity. 7 times 60. So this is the amount of saving of electricity if when you introduce the soft switching in this laptop chargers. So you save 60 times 7 trillion watt-hour of electricity. So you can draw how much carbons we have saved. Because this 7 times 60 trillion watt-hours have to be generated from coal or gas or petrol. You see the amount of saving, and you can see the impact of power electronics. Small change. Just changing the circuit topology from hard switching to soft switching. Before we switch at any voltage, any current. Now we switch at 0 voltage, 0 current. That's the loss. And you can see the impact. So, and as I say always, you look into the global perspective. Don't look at yourself. Don't look at 15 watt. What is 15 watt? Is that maybe in 1 year it costs you maybe alpha about 3 watt. But when you look at it globally, then you can see the impact of emissions. So this is one example, very small, simple example. I'll give you another example. This is applied also for all data centers. So let me give you an example. This is data centers. Data centers are becoming very, very important. Data centers, like Google, NCETEE, Microsoft, X, Facebook, they have a lot of data centers, banks, online transactions. So they need to have a power supply 100%, not 99.9. The power supply has to be supplied 100%, all the time, whatever happens, because imagine Google goes for 1 minute, or less than 1 minute, 30 seconds. You know how many billions of they will lose? Billions of dollars. Like Amazon. All these big companies, they invest a lot of money in data centers, and storage. So they have what they call the UPS system. And this UPS system for these data centers, and it's mentioned somewhere here. Yeah. Data centers will consume 10% of the electricity generated by 2025. So the amount of electricity that will be consumed by these data centers will increase because, the cloud, you see clouds, these are all data centers, So the consumption of electricity will significantly increase. And this is the architecture of the existing data centers. What we have the grid, and then we have UPS systems, which is conversion from AC to DC, DC to AC, and then storage. And then we have the servers where we have the voltage regulators that supplies the required voltage. Can you see these green boxes? These green boxes are conversion, right? Every time when we do conversions, we have losses. There is no 100% efficient conversion system. So far, it does not exist. You can achieve 99%, but there is always losses. So you can imagine 1, 2, 3, 4, 5, 6, 7. There are 7 conversion states. Assume, in the best case scenario, each stage there is around 3% to 5% losses. So you're talking about how much? 30% losses in the system. So what happened, starting from this year, 2023, Google already have moved from this architecture to what we call DC data centers. Why we have to do conversions? So what we do here, instead of doing this, so we have one converter which is AC to DC, and then storage, and then goes to all DC. Because inside the server, it's all DC. Why do you have to use AC? So we remove, how many stages we remove? We remove few stages of conversion stages. One here, one there. So it's almost the saving, it's around 5%. amount of saving. Just removing 2 conversion stages. And this is equivalent to what's generated by almost 15 nuclear power plants. So moving from AC to DC data centers can save us a lot. How about if we change this grid with the PV? If we change with the PV, we don't need the AC to DC anymore. We can supply directly to the batteries and then supply to the system. So, and 5%, I'm talking about 5%, maybe less than 5%. You can see the amount of saving that we can do. The other example, which also power electronics plays a major role, is lights. And you can see how many lights here. It's a lot of lights. And if we use more efficient light bulbs or more efficient devices, see the amount of saving. If we move from this part to the saving, we can save around 20%, 20 times energy efficiency. And you can see the amount of saving. It is estimated to be around 450 nuclear power plants. I know switching to LEDs is not cheap, it's expensive, but if we do it gradually. For example, we have this lecture hall, I think it's all LEDs, I hope so. There's a blue line, but so if we use LEDs, that's the amount of saving. And LEDs what? An LED needs an LED driver. LED driver is power electronics. You can see the impact that power electronics can have in saving the electricity. The other big, I call big brother, which is the motor drive. 60% of electricity generated actually it comes from, it's used in motor drives in industry. Most of the electricity, especially industrial, I'm talking about industrial countries. In Algeria, maybe it's a bit different, but if you look into the United States, 60% of electricity generated is used in industry. The other 40% is used in domestic, transportation, commercial. 60% goes to industries. In China, the same. In Europe, this is the same. So there is a big electricity consumption in the industrial sector. So if we use what we call VSDs and VFDs, variable speed drive. Okay, and this variable speed drive also is used to try to reduce the energy consumption in electric motors. We can save around 30%. I'm talking about motors which doesn't operate at full load, because if the motor operates at full load, we don't need VSD and VFD. But if the motor, the load is changing, so VFDs and VSDs are important to energy saving. So, very important. And this VSD is what? It's a rectifier and inverter. You have a fixed, voltage fixed frequency. You put it inside the VFD, you generate a variable voltage, variable frequency. It's a power electronics. So there is a lot saving in this motor drives. Okay, so this is some examples that you can see the impact of power electronics in trying to reduce or use the electricity more efficiently. Is to try to be innovative, and I think in the last 20 years, power electronics has been dominant components in our appliances and our loads. Also in terms of renewables, I'm talking about renewables. So in renewables, you can see there is a tremendous increase in terms of renewables, in terms of solar, wind, and all other appliances. I'm going to go through fast this one. And I would like to mention here, you can see, for example, the use of renewables is increasing, and the use of non-renewables is decreasing. So that's a good sign. We hope one day we will reach to the zero non-renewables. If you look into the wind, and wind energy, you can see wind energy reached almost 900 gigawatts. But the good thing about it, one single wind turbine is able to generate around 50 megawatts. And it's 100% power electronics driven. What does this mean? means now we have reached a stage where power electronics devices are able to handle high power, 15 megawatts, single megabyte. What does it mean? It means the components, especially with the introduction of the silicon carbide and the GaN devices, actually enable us to operate at very high frequency, very high current, and very high voltage. So this is the main breakthrough. You know, you can look into in the 90s, the use of power electronics is zero. We moved to 100%. And this is the development in the semiconductor technology. Is the semiconductor devices are becoming what we call very able to handle, and also the control. We have very high processing powers and very sophisticated powers. So in terms of wind, it's all power electronics. The same thing goes for photovoltaics. It's increasing year after year. And if you look into the photovoltaic system, it's the same. We have the renewables, and then the interface. It's always power electronics. You need the power electronics to generate the power of the PV. Wind, I think I mentioned it now. I'm not going to go in details unless if someone has specific questions. I know we come from different backgrounds. I try to keep the presentation as general as possible. But if you have specific questions on specific topics, I will be more than happy to address it. So in terms of wind, there are different types of configurations that we use. You can see either it is partial speed converters or full speed converter. You can see the second diagram, 15 megawatts goes through this AC to DC and DC to AC converters. And this is a major breakthrough actually in the design. There are different types of topology that we use, either low voltage or high voltage topologies. I will try to move. For the PV also the same. We have different topologies, from micro inverters to central inverters. We're talking about a few hundred watts here, few hundred watts to megawatts. Okay? And each one has pros and cons. If you ask me, for example, which one is the best, it depends what you are looking for. If you're looking for the cost, then the central inverters are the best. In terms of performance, maybe micro inverters will be the best, but they are expensive. So there are different, what we call, selection criteria that will be applied in the selections of these devices. In terms of grid connections, we have different types of way of connecting to the grid, either through a transformer, low frequency transformer, high frequency transformer, and also even transformers. But also there are issues that we need to address, such as the leakage current, common mode voltage, and so on and so forth. There are few topologies also. I'm not going to go through this. And the recent one, which is the hydrogen productions, where we see a lot of countries are pushing for hydrogen and green hydrogen productions, is still not economically feasible because the cost of generating hydrogen is still very expensive. But and then in the future we will try to minimize. And then we have the photovoltaics. Photovoltaics 20, 30 years ago was very expensive. In the 1970s, the cost of 1 watt was $75 per watt. Today, 10 cents per watt. We're talking about the span of 50 years. The costs have reduced from $75 per watt to 10 cents. And that's what happens in every technology, because the technology measure in hydrogen productions, we need to power the electrolyzer to generate hydrogen. So we need the power electronics. And there are many the existing topologies using either the SCR rectifiers, different 12 SCRs in controlling hydrogen productions, but they have problems with very bulky because of transformers, large transformers, large big transformers. So we try to look into what will be the best solution to eliminate all these transformers. Because very huge transformers, and also they generate a lot of harmonics because we're using the SARs. Then move to using the IGBTs and MOSFETs. That improves a bit power quality, but still the transformers a big issue. And the most recent one is using MMCs, multi-modular converters. And here we managed to eliminate 100% transformers. So we don't need the low frequency transformers, which are very binding. And this is the trend now, which is modularity, scalability, and fault tolerance. Because through these MMCs, we will have modularity. It means modularity is a multi-level. One module failed, and plug. One, for example, the system still works, maybe at reduced power, but still continues to work. So it's modularity, scalability, and fault tolerance. Scale means I have 5 megawatts, I want to make it 10 megawatts. Very easy. Cost is cheap because you fabricate the same modules. Okay, so that's modularity, scalability, and fault tolerance. Professor Cree, tell me the time. Yeah, because we lecturers, we make money by talking. It doesn't stop me and we continue talking until tomorrow. You just tell me the time. So this is the time the transformers. So maybe the last few slides, I would like to share with my colleagues and some of the students the outlook. What is the new area of research focus now? Because we need to, when we do research, we do the research of the current problems. We do research for the next 20 years problems. We can address the current issues. The current issues already have solutions, and maybe people. But as a researchers, we always look into 20, 30 years back. It's coming, the future. And that's very, very important to look into this. One of the focus areas in the power electronics is hybrid inverters will become more popular. Inverters usually they used to convert AC to DC. That's the first time when we do it. And then able to inject active power. 5 and must be the total harmonic distortion must be less than 5%. That's the requirement. 5 years later, then we see the requirement is now able to active and reactive power. 5 years later, then the quality of the waveforms able to communicate with other inverters. 5 years later, then maybe the inverter must have an MPPT, maximum power point tracker. 5 years later, the inverter must have battery charging because most of renewables will have storage. So the inverter should be able to act as charge controller. So the future inverters will not be just an inverter. It should be able to do active, reactive, and the most challenging one is to be able to inject power and control stability of the grid. Because the previous inverters are grid following. Grid following means they follow the grid. Means we assume the grid has stable voltage, stable frequency. And then we use the phase loop rule, and then as a reference, and then we inject the active and reactive power. But the new inverters, and this is also very hot topics, which is grid forming inverters. Means the inverter should be able to help stabilize the frequency and the voltage of the grid. Means you connect to any voltage, any frequency, and help to stabilize the frequency and the grid. Because the grid now, it's becoming less what you call inertial. There is no gas power plants. All of them are inverters or renewables. Who is going to stabilize the grid? There is no large power plants. So everyone is solar, is intermittent, keep changing. So the requirement of new inverters have to be grid forming. And there is a lot of work actually in this topic. The other topic, it's this way called DC nanogrids. If you look into this slide, you can see the current practice. The current practice what we have a grid, PV, wind, storage, electric vehicles, and then in the bottom we have all the appliances. So what we do actually, we generate power from the PV, and then what we have? We have DC-DC converters and then inverters that connect to the grid. The same thing goes for the inverter, for the wind. The same thing goes for the storage. And then we're going to use it because most of the appliances are inverter based, right? So we convert to DC again. So we have conversion on the upper side and the conversion on the lower side. And as I said, if only assume 1% or 2% losses, you just multiply. So the new trend is to move into what we call DC nanogrids. DC nanogrids means, since the supply is DC, the nodes can operate on a DC. Why do we need inverters? You don't need them. You just need to create a DC bus, the DC voltage bus, and then you connect your appliances to it. Because your light is DC, your TV, LED is a DC, your fridge is DC, your washing machine is DC, your cooking, induction cooking, is DC. Your car is DC. Why do you need AC? So this is the future. The future will be for DC. And I give you an example, some in many countries, for example, I give you an example in Australia. In Australia now, new house, it's in the guidelines for building the house. It's required. No stove with gas, not allowed. You must have induction cooking. Every house must have electric vehicle charging. You have a car or you don't have a car. You must install it. So the future is moving into this. So what you can see, even within the house, you can run on a DC without any problems. But this requires a lot of investments. To move from AC to DC requires a lot of investments. But there is a lot of work, research on harmonizing AC and DC to work together. We call it harmonizations. And we have DC nanogrids, AC nanogrids, and then how they can operate together. So this is a new focus area, which actually it's a good topic, and there are a lot of work on it. The other focus area, which is electric vehicles, and in Nigeria or anywhere in the world, I don't know in Nigeria what's the plan, but many countries already put a deadline. For example, in Australia, they say by 2035 there will be no new car. They will not allow any registration of new car, gasoline car. 2035. What does it mean? You can have a car, you can have it for up to another 100 years, but you cannot sell it. You cannot buy a new car. Whenever you want to buy a car, it must be electric vehicle. I think a few countries have already announced. I know, maybe not possible, maybe 100%, maybe they achieve 60%. They have a plan. Everyone has a plan. If you achieve 40%, 50% is good. Maybe you will happen at 2035, it happen at 2040 or 2050. But it will happen. And you can see the houses starting from 2024. Every house built new must have charging station. You have a car or you don't have a car, you have to have it. It's a requirement. And this is a very hot topic actually. And in electric cars, electric vehicles, there are lots of research focus areas. One, for example, is the optimum. I know the infrastructure needs to be built, but for example, what is the location of the charging stations? Where you put them? You put them in the city, on the highway, in the shopping malls. So there's a lot of research on the optimum location of charging stations. This can be done, you know. Another topic, which is fast charging. Fast charging means the electric vehicles currently can go up to maybe around half an hour. You reach 80% charging. So there's a lot of focus on how to design fast charging electric vehicles. Means within 10 minutes you can charge the electric vehicles. Fast charging. DC versus AC charging. There's a lot of work. The impact of charging on the grid. Because imagine you have hundreds of cars or thousands of cars connected to the grid, enjoying high current, high voltage. What will happen to the grid? It will collapse. The grid will collapse. So you need to define a mechanism. How are you going to charge? Maybe some cars are charging, some are discharging. Yeah, because that's, and electric vehicles will play a major role in becoming what they call mobile storage. Mobile storage means charge during the day at your office, because, for example, you park your car outside, it's charging station by solar. At night, when you go home, you plug your car to the house. So your car supplies electricity to your home. Because the price of electricity changes. You know? I don't know, in Algeria it's fixed. But in Australia, for example, price of electricity can go from negative to almost 20 cents per kilowatt hour. Negative, what does this negative? It means they pay you when you use electricity. Midnight, for example, 1 o'clock, 2 o'clock, 3 o'clock in the morning, no one uses. Electricity it's free, not free actually. You make money by using electricity. So how you can charge your car and discharge, when you charge and discharge. This is a lot of studies works in. And there is another topic which is the wireless charging of electric vehicles. I recently had a few projects, around $5 million project on this, on designing wireless charging. Because we believe the future, and as I told you just now, we work on the next 20, 30 years project. Wireless will be the way. Because when you have an electric vehicle, electric vehicles made in Europe, in China, in US, in Japan, in Australia, everywhere. Different standards, different blocks. You need to have a adapter everywhere you go. So what we see, the future will be for wireless, means when you park your car, you don't have to do nothing. The power will easily transfer from the coin. There are a lot of challenges in it. Even I think it's already applied in the phones, but we are talking about 20, 40, 80 kilowatts system. You know, I'm not talking about low power. Low power is already mature technology, but we are now working on high power applications. So wireless charging, and in wireless there are two. We're talking about static and dynamic. We're looking in the future where the car moves and is charging. Means, for example, we have Imanef Jazair and also Zair, Mustaqil Zair. And the Kawalin, one of the lanes is wireless charging. So your battery low, move to the other lane. The problem of battery. So university, which was moving dynamic wireless charging of energy. I see like in the next 10 years to 15 years. You know, in 1996, you remember when we started? Okay, it might be able to connect to the internet. Just show me new laptops have a LAN port today. None. All new laptops. So it's the same, the transitions will happen in the power area. So we will move to wireless. It will have a lot of issues, a lot of problems, but it will be the new future. Energy storage, another focus area which is a lot of work actually is going on in energy storage, because as I said, we're moving from traditional to renewables. Renewables will never work without storage, because of the intermittent nature. We need to store the energy. Wind or solar need to be stored. So there is a lot of work on the storage devices. The device itself is the types of batteries, the types of maybe hydrogen, maybe different types of storage technologies. So this is people from materials, people from chemistry. I think it's very important to look into these areas. And let me show you this, maybe one of the last slides. This shows the trend of the electric vehicles. It's expected to reach around 100 million cars by 2030 or 2035. Electric vehicles. You know, the estimation of the current fleet of electric vehicles will reach around 100 million cars. That's very good. But the issue is, what we're going to do with the batteries inside these cars? You know, we have 100 million cars. Every car, how many kilowatt hours of batteries it has? Because the life battery of these cars will run between 10 to 15 years. What are you going to do with all these batteries? Are you going to throw it inside the environment, so it causes a lot of problems? What are you going to do? So this is a new focus area, which we call them second life batteries. These batteries need to go another life. We call them second life. Because in order for us to reduce the environmental impact, we need to extend the lifespan of these batteries as much as possible. So what will be the potential application? Stationary application, renewables. Because most of the batteries will retire when they reach 80% of the initial charge in the cars. When they reach around 80% of their charge, state charge, they will be replaced. 80% is a good, still can be used in renewables. But there should be a research, because these batteries made from different manufacturers, different technologies, different state of health. So we need to do sorting, we need to test them, and then put them together and then storage them. And this already started, you know. We have, in Australia, there are more houses have renewables, have solar. But the problem in solar in Australia, when you buy electricity from the grid, is around 25 cents per kilowatt hour when you buy. When you sell from the solar, 5 cents. Cheaper, you know. You understand that, you know, because it's an investment, everyone has solar. So when you want to sell, it's 5 cents. When you need to buy, 25 cents, 5 times. Yeah, because the market is free, you can change. You don't want to connect the grid, you have different suppliers, you can switch. Today I have this, tomorrow I will switch, depends on the price. So what we are doing now, we have what we call neighborhood storage. Small, around 15 houses, we will have this container. We have second life batteries, we store energy. So we don't sell to the grid. We store all the neighborhood, we store the energy. And at night we use from the storage. So neighborhood storage. And all using second life batteries recycled from the electric vehicles. So this is another area. And in the batteries, there are many issues that need to be addressed, especially the BMS, the battery management system. And there are many issues because they are second life, means you expect to have a lot of problems. And one of the suggestions we have made to the car manufacturers, all the new cars, EV cars, the new ones, need to have data logger, memory cards with a battery system to store the data of charging and discharging. So when we recover these batteries, we have this memory card, we read the data, we know how the battery gone through. for the last 10 years. So we can combine it with another connector. So this is another very hot topic, especially on the protection, performance, optimizations, and also the calculations. And there are also few ways on how we combine this. We call second life batteries, a different approach. Either we use a single central inverters, or we use what's called a modular, or we use power electronics devices where we have some sort of like an MMC. If you look at it here, it looks like an MMC. Similar to the MMC. We have different battery cells, and then we are connected to the fridge. I think that's my last slide. So in conclusion, the reduction of emissions, like we have seen before, and I've given you some examples how power electronics can help achieve neutral carbon society. We see that from the scale level, from small scale level, may not be visible, but if you put it at a global perspective, you can see the impact as engineers. And I know many of you, maybe they are chemists, people are maybe in different areas, they can have their own contribution. So I'm making publicity to my history, power electronics, but I think every one of us has a role to play and has different one. Even the people from literature, people from arts, when we build the neighborhood batteries, what to do? The container doesn't look nice. So what do you call? We call artists. We call the artists to come to decorate this container to look nice. And then people will come take pictures now next to the batteries. So every one of us has a role to play. People from forestry. So we ask them, what will be the best trees to plant around this neighborhood battery? So in terms of this kind of research, actually it should be a multidisciplinary, and people will appreciate this. Now, so that's my conclusions, and I will be more than happy to answer any questions you have. Thank you very much.
Thank you very much, Mr. Saad, for your very interesting presentation. Now, are there any questions? Professor Saad?
Yeah. I'm so happy. Like I said, not only questions, but also comments. And if you disagree with me, not only questions, because questions you suppose I know better than you, but it's not always the case. You may know better than me in certain topics. So if you have comment or you have different opinions, you are welcome. We are scientists. We should be able to debate and discuss and take the best solution. So don't only questions, comments, whatever you have, different opinions, is welcome. Please.
First of all, I would like to thank Mr. Saad for his presentation. Just concerning storage systems, I'm interested in this subject, in this research. What do you think about influence of batteries types on our environment, like pollution, and so on? Just concerning lead-acid batteries or lithium batteries? Thanks.
Yeah, I think very common question. Very common questions that the impact of batteries on the environment. Because we know, first one, the batteries, for example, lithium ion are made from rare earth materials. Lithium ion is made of rare materials. And they are very expensive. We have to mine them. So there's a lot of energy used during the mining. And then we have problems when they finish their lifespan, to throw them away. And that's what I mentioned just now. Every technology that we introduce, there will be effects. But what we do, we calculate the impact through the life cycle, the total life cycle. For example, include the emissions generated during the mining, during the then calculate the amount of emission that's produced, and then if we do nothing, compare it if we do nothing, we still burn the gas and oil to generate electricity. What will be the amount of emission? You will find, I'll give you an example, very simple example. The electric cars. It's an analogy, it's not batteries. That's why in the battery you try to extend the lifespan. The longer you extend, the lower impact. There will be an impact. Okay? Then I give you an example for electric cars. Many people say, if we use the electric cars and then we charge it from electricity, this electricity is generated by burning the gas. It doesn't make sense. You understand? We did study, my group did a study. What is the amount of energy available in 1 liter of oil or gas? Okay? Liter. This one. Okay. 1 liter. How many kilometers you can go? Depends on the car. If it is Ferrari, you just press, it's already gone. Not move yet. So, depends on what type of the car. Right? So let's assume that says 10 kilometers. 10 kilometers. You have to know what's the efficiency of the IC engine, the internal combustion engine. We're talking about 40% in the maximum. So 60% actually is a loss. We use that 1 liter, we burn it, we generate electricity. We can go 16 kilometers, 60% increase. You understand? The same thing. 1 liter, we put it inside the IC engine, internal combustion engine, it takes you 10 kilometers. We use that 1 liter, generate electricity, store it, use it in the electric car, you can go 16 kilometers. We already calculated around 65% improvement. And the same happens for any other. That's why the way forward, as you know, the way forward is what we call electrification. Don't think about the soft yet. Think about electrifying the load, for example. That's why cooking, transportation. Transportation is a major contributor to the pollution. So we need to electrify the transportation. And when I say transportation, don't think about the cars only. Airplanes. How many thousands of airplanes, How many ships, cargoes, transportation of ships and goods. What they call trucks, long trucks, long distance trucks. That's a lot of emissions happen. And currently, the only sector that is lagging behind in electrification is the transportation sector. You can see industries, they move to motors, using motors, electrifications. What they call homes, we move from gas to electricity. We move, even heating, we are moving into electricity. Water, moving into electric water heating, because that's more efficient. Okay?
We have time for 2 other questions.
You can ask in any language, so you can ask in Arabic, in French, in any language. Maybe some people I think I can answer, no problem. So Algerian speaks all languages.
There's a question here.
Yes.
I have a question about your project of wireless charging. I think you said that vehicles and highway can charge. I think when the distance between the vehicle and the ground is, we have variable distance, and the long distance there is a lot of losses of energy. So how you fix this problem? How do you think to fix this problem?
Very good question. This is the biggest challenge for wireless charging. In wireless charging, you mentioned one problem, I will give you other problems. So one of the problems is the distance. Because this is inductive, it's like transformer, the only thing we put them apart here. So what we do, we increase the frequency, okay, and then we generate the electromagnetic field and then we capture it in the secondary side. It's the same principle of transformer. So this amount of the recapture of the electromagnetic field that generated depends on the distance. The more distance, the higher losses. That's one of the big problems. So we try to optimize what will be the best coil shape design. We look into the coil. We say the coil, we have a transmitter and receiver. We look into what the best coil and how many coils. Is 2 coils enough, or we can add another in the middle? When I use in the middle here, not in the middle between the car. In the transmitter, there is another coil acting as a buffer to amplify the magnet. So we're looking into different types of shapes. What will be the shape? Is it circular? Is it rectangular? Is it D? Is it Q? We have analyzed different types of coil shape designs. This is one of the problems. The other problem is the misalignment. Because you have coil already fixed, right? When you drive, not all the cars are always like this. You may move left, right. So this is another big issue. How to address the misalignment issues, because the maximum power transfer happens when the coil, the transmitter, and the receiver is right on the top of each other. You move like this, you have lost. Like this, you have lost. So we have also we have 3 patterns on what to reduce the misalignment issues. So there are, research. We researchers, we never solve problems. We create problems. When we solve one problem, we create another problem. Otherwise, we have no job. If we solve all the problems, tomorrow we have no job. So we should keep solving. And if you look into this, topology, it's really very simple. You have a DC inverter, high frequency inverter, and then you have the coils, the primary, that look like transformers. And then we have the compensation circuit, you see? The LC, the compensation circuit. So there are different types of compensation circuits that can be used to minimize the impact of distance and also misalignment.
The last question.
Yes, there are 2 questions. There are female, I think we need 2 questions.
In every technology, there's a person with this specification. Nous remercions pour votre exposé. Donc, in every technology, there is a pessimist and optimist. Like the vehicle cars, there is sufficient resource like lithium in nature to fabricate all these batteries. Because the idea, the political idea or the scientist idea is there is not sufficient materials in the earth to give oil pour aller des énergies fossiles vers les énergies renouvelables. Que la guerre, maintenant nous avons des guerres de pétrole, et dans 10 ans, 20 ans, nous aurons des guerres de lithium. Est-ce que c'est vrai? Parce qu'il y a suffisamment de ressources naturelles pour fabriquer ces batteries, pour aller vers ces véhicules électriques, etc.
Yeah, I think I agree. Thank you very much for the question. So the challenge is, do we have enough resources? We have enough rare, like I said, the lithium ion is made of rare earth materials. So do we have enough? I'll give you an example. We are moving from lithium to solid state batteries. Toyota announced in 2024 they will be producing Toyota. If another car manufacturer, maybe I will put a big question mark, but Toyota is a big company. They say 2024 they will introduce the first electric car using solid state batteries. No more using lithium. So that's what I say. Every technology requires some time. We will not, the amount of iron, lithium ion available in the nature is not enough to generate 100 million cars. I know. But with the time, there will be innovations. People making one batteries, they will look into new materials. I give you an example for solar cells. Solar cells, we use silicon. I know silicon can be made from sand. But now we have organic solar cells. Organic. You can make it from the kitchen waste. You can make it from different materials. So the technology is actually when night side, when there is a lot of demand, so there will be a few years back we only had So there will be innovations on reducing the amount of rare materials. There will be new types of batteries. There is a new technologies. For example, the many series actually cars, electric cars based on the batteries is just a transition. The future will be for hydrogen cars. Possible, but there are challenges to address: storage, generation, transportation of hydrogen. There are a lot of issues, but there will be, because there is investors. People will invest in it. Yeah. Other questions?
That's the very last question.
Yeah, please.
Assalamu alaikum. I would like to thank you for your presentation. I have a small question to speak about solar energy and wind energy. I saw a documentary about getting energy from ocean and wind. Yes. Are there researches about that?
Yeah. There are quite lots of actually research on different technologies, from wave energy, from I call geothermal, different technologies. Actually, not only wind, but why wind and solar? Because wind and solar are becoming economically visible. Wave energy, yes, there are quite a number, but they are demonstration, research-based projects. Have not reached to the commercial level. If you ask me, what will be the cost of kilowatt hour generated from photovoltaic? It's cheaper than the one generated from gas. Not in Algeria, because Algeria they subsidize the gas. But if you go to Europe or to Australia, the kilowatt hour generated from solar is cheaper than the kilowatt generated from the gas. Because it's economic. That's why they invest. They make money. So only the electricity from wind is cheaper than the power generated from gas and coal and things. So that's why it's becoming feasible. But there are other technologies. There are many other technologies which can be used, like wave energy, even the undersea. Is undersea water, movement of water, can be generated electricity, but it's still not economically. It's not economic, but there are like demonstrations, like it's chimney, chimneys for solar. There are not, but it's only on demonstration. Yeah.
Thank you, Professor Saad. Now the session is closed. Thank you for a very interesting presentation, very instructive. I think everyone have enjoyed it. And now we have the pleasure to give you a certificate of participation. Thank you.
Step.
After the break, there will be a poster session.